Right. In this video, we're going to take a look at something known as a differential, right? And it's basically a new take on an old concept. How old? Well, it goes all the way back to the definition of the derivative. Now, remember, when we defined the derivative, we actually started by looking at a secant line. So let me remind you of that oldie but goodie, right? So you have a curve, and the secant line is a line that passes through 2 points on that graph, right? So we have an A and we have a B, and hence a F of A and an F of B, right? And we have our secant line. And what we said was, and if you remember, we introduced this notation, we call that, what is our run? We just call that delta x. And then the rise, which is this, we'd call that delta y. And then the slope of our secant line is simply our rise over run, or delta y over delta x. But another way to think of this equation, right, and remember these deltas are just changes. So this says the change in y divided by the change in x, or you could say this, the difference in y divided by the difference in x gives us this slope of the secant line. But we can actually rewrite this, and we can say that our change in y, or the difference in y, is equal to the slope of the secant line times the difference in the x, right? So, I mean, it's just algebra, right? On this side, I have a fraction, right? These are two numbers, and then I can multiply both sides by the denominator. So as long as the denominator is not 0, then everything here is valid, right? So it's just another way of looking at it. Well, if I can do this with the secant line, why can't I do it with the tangent line? Well, that's where it becomes a little more conceptual. But let's try to mimic this, right? Let's try to mimic this. So if I have my graph, and now for the tangent line, let's say I put the tangent line right here, like that. So that would now be my A. Well, the problem is I don't really have a second point, right? However, what I could do is I could just pick another point here, right? And say, okay, and then, so whatever this point is, and say, okay, well, that would be my run, and then that would be my rise, right? But we know, so then if I wanted to find or write down something for the slope of the tangent line, but we know what the slope of the tangent line is. That's the derivative. So I can actually say that this is dy over dx, right? But it's also our f prime, right? So it's also our derivative evaluated at that point, right? So if I call this now my dx, so if I call this distance my dx, and then that distance my dy, then I could come up with something similar to this. I could say that the slope of the tangent line is equal to, which we know is true, dy over dx, right? And that's also my f prime at A. So again, as long as my dx is not 0, I should be able to do something similar to this, right? So I could say, so therefore, dy is equal to my derivative evaluated at that point times dx. So it's now basically saying that, this quantity, whatever it is, because now we've kind of separated it from the dx. We've always just kind of written this as one thing, but now we're actually saying that we can envision this dy as being equal to our derivative times dx, just like how my delta y is equal to the slope of the secant line times delta x. So this is the quantity that we define as a differential, right? So let's write that down. So given a function y equals f of x, if f of x is differentiable, again, we have to make sure that the derivative exists before we, define a lot of these quantities. So if f of x is differentiable, we define the differential of y. So the differential of y as dy equals f prime of x times dx, right? So we refer to this as the differential of y, and it's equal to the derivative of my function times the differential of x. So these are now differentials. So this is the differential of y, and this is the differential of x, right? But what it is just a different way of thinking of the derivative. So this dy over dx, and instead of thinking of it as a slope, we can now think of it, for instance, over here as like the product of two quantities, right? And in a second, we're going to see how the delta y and the delta x are actually related to the dy and to the dx. But before we get to that, let's just do a couple examples just to show you that, again, it's nothing new in terms of a process, but it's a new concept, the way we interpret this derivative, right? So let's do a couple examples here. And for each of these, what we're going to do, find dy, right, of each of them. So let's say y is equal to x squared times the sine of 3x. And now I want to find the differential of y. Well, you can do it in two steps. I will do my regular derivative, just write it like that. And then on this side, I have to do my product and chain rules. So this derivative is 2x times the sine of 3x plus x squared. And then the derivative of sine of 3x is 3 cosine of 3x. Now the new thing is I now have the ability to essentially solve for dy dx. Oh, sorry, for dy, or just say isolate dy. So I can say that the differential of y is equal to this quantity. I'll put the 3 in front, so 3x squared cosine of 3x, and then all of that times dx, right? So, just to kind of remind you, this is that Leibniz notation, right? And then we now refer to this as the differential form of the derivative. So this is an example of a differential form, right? But process-wise, nothing has changed. Let's do another one. So let's say we have y equals the square root of x over, let's say, the arc sine of x, right? So remember, this is an inverse function. It's not a reciprocal. So let's set up. Now, since it's set up as a quotient, I'll just go ahead and use the quotient rule. Good reminder of a rule. So the derivative of the numerator is 1/2 times x to the negative 1/2 times the denominator, so that's arc sine of x, minus the numerator, so that's x to the 1/2, times the derivative of the denominator, and if you remember, that's the 1 over the square root of 1 minus x squared, and then it's all over the denominator squared. So kind of a messy derivative, right? I'm not going to even worry about simplifying this, but now if I want to write this in differential form, all I have to do is take dx and multiply the entire expression on the right. So I have my 1/2 x to the negative 1/2 times arc sine of x minus x to the 1/2 times 1 over root 1 minus x squared, all over arc sine of x squared, and then that times dx, right? So if you can find a derivative, you can find a differential, right? At least this kind of differential, all right? Well, what is the benefit of doing something like this? Well, previously, I drew, the secant line and then the tangent line on two separate graphs, right? But let's put them together on one graph now. Because if we want to find a relationship between the two, let's see them both, right? So let me start with first I'm going to start with the tangent line. So let's say my tangent line is right here. Let's make that a little like this. And then for the secant line, I'm going to have it pass through this point, but then another point here. Well, actually, I'm going to make it kind of close. So like this, right? So let's write down what we know now, right? So we know that the slope of our tangent line, we know that is dy dx. And the slope of our secant line, we know that is our delta y over delta x. Now, as far as the delta x is concerned, so here is the point of tangency. That's a little hard to see. And then for the secant line, this would be the second point. So this would be my delta x. And it actually turns out it would be the same as my dx, right? So that would be the run for both of them. The rise would be different because the tangent line only goes up to this point, whereas the secant line goes a little higher because it's on the curve, right? But regardless of the little picture there, that's a little hard to see, but the important fact is that if you look at the slope of the green line and the slope of the blue line, they're not identical. But if my delta x is small, right? So in other words, if the second point that's on the secant line, if it's close to the point of tangency, then these two slopes are going to be pretty similar. In fact, we could say that the slope of the secant line is an approximation of the slope of the tangent line. So let's write that down. So when our delta x, which is the same as our dx now, is small, and again I'll put this in quotes. What do we mean by small? Well, we have a relative idea of what small is, right? So when this change is small, when the change in x is small, the slope of the secant line is approximately equal to the slope of the tangent line, right? So my difference in y over difference in x is approximately equal to the differential of y over the differential of x. But what else do we know about the derivative? Well, at that particular point, right? So we know that the way we would actually compute our derivative, or even another notation for the derivative, is by taking our function, finding the derivative, and then evaluating it at that particular point. So let me just call that point x0, for instance, or I could call it a, right? So that means the change in my y divided by the change in x is approximately equal to the derivative at that point. Now, if I do the same thing that I did earlier and take this denominator and multiply both sides, I have a pretty useful relationship. It says that the change in my function, my y value, is approximately the slope of the tangent line times the change in my x. So if I wanted to approximate the change in my function, then I could utilize this result, right? So let's put these two things together now and look at them, right? So we have that our differential form looks like this, and then we now have this approximation that looks like this. Oh, I need my approximate there. All right, equal to delta x. And we're saying that these two things are equal, but these two things are not necessarily equal. Just looking at them, you can see that the rise on the secant line is not the same as the rise on the tangent line. So these are kind of the two important equations that are related to this concept of differentials, right? Let's do an example that now utilizes this concept. All right. So here's another example. All right. So it's going to say use differentials to approximate the change in y equals, and let's pick this function like the cosine of, actually let me write it on the next line. So here's my function. So use differentials to approximate the change in y equals cosine of x squared plus 1 minus 1, or minus x, as x changes from x equals 2 to x equals 2.03, right? So we're going to use differentials to approximate the change in this function as x changes from 2 to 3 to 2.03, all right? Well, that means we're going to utilize this formula, right? We're going to utilize this formula, and so based on this, this would be my x0, because this is the starting point, right? And then I can figure out the delta by taking the difference in the x values. That's what my delta is. It's the change in your x. So let's write this down. So the change in x is the final x minus the initial x. So 2.03 minus 2, so that's equal to 0.03. And you can see that this is a small change. This is a small change, right? And then, so now in order to use differentials, see what the equation says is that the change in y can be approximated by my derivative evaluated at the initial x times my delta x. So I have my delta x. Let me state what my initial x is. It changes from x equals 2 to x equals 2.03, right? So here's our x0, if you will. Here is the delta x. Now I need my derivative. So let's differentiate this function. So dy dx is equal to, so we need our chain rule here. So negative the sine of x squared plus 1 times 2x and then minus 1. All right. So let me write it like this. I'll put the 2x in front. So this is negative 2x times the sine of x squared plus 1 minus 1. Okay. Well, now we have this other way of writing the derivative. So I'm going to say that dy is equal to all of this times dx. So negative 2x sine of x squared plus 1 minus 1, and then that's all times my dx. So that's the differential form. But now we can also say that the change in y is approximately equal to this thing times the change in x. So basically what happens is when you replace the d's with deltas, you go from something that's exact to something that's approximate, right? And that's why it's good to think of those two equations, together, right? One gives an exact relationship, the other one gives an approximate relationship. All right. So there we go. So now we get to plug in our values. So when x is equal to 2 and delta x is equal to 0.03, then delta y is approximately, and now we plug everything in. So we'll have, so I'll plug 2 in here, so that becomes negative 4. And then in parentheses we have 2 squared plus 1, so that's 5. So the sine of 5, and then minus 1. And then put the change in x, that's my 0.03. And then when we evaluate this, now it's important to make sure that we utilize radians, right? Make sure we use radians. And then that gives us 0.085070913, and so on. So again, if we're on the graph of this function and we're starting at an x value of 2, if we increase our x value to 2.03, then our y value will increase by approximately this amount. So this number here represents the approximate change in my y value when I start at x equals 2 and I increase my x by this amount, right? So it's actually the amount by which the y increases, that's the rise, right? And we're able to use the derivative to approximate it, all right? So those are two, again, different ways of looking at the derivative, and now the idea that we can think of dy and dx as separate quantities is a big conceptual step forward that we will utilize quite a bit in the future. All right, see you in the next video.